everyone. So this is going to be about lecture 11, so that's about bonding. I'm Lillian, I go by Lily. Yep, that's all you need to know about me and what we're about to do. Let's get started. So terms and concepts, I kind of compiled a list here of all the things that we're going to be talking about during this review video. So I'd recommend, watching this and then coming back over here and making sure that you understand what all of these are. They're not all in order, I realize now, but hey, that just makes it better for studying, right? Okay, so let's start out with the structure. So how does bonding affect structure? So bonds give structure to molecules through the spatially arrangement of atoms. But before we go into the types of bonds, I want to kind of talk a little bit more about that. So so bonding in general is basically the electrostatic attraction holding two atoms close together. And the reason that they form is due to the difference in the changes between the negative electrons and the negative electrons surrounding the atom and the positive protons in the nucleus. Yep, fun. We will look at why it is beneficial to the energy stage to form bonds in the next slide. But for now, let's talk about these different types. So basically, here we have ionic, covalent, and metallic. So we can tell. Okay, so we can tell the ionic and covalent bonds apart from the electric negativity of the atoms forming the bond. You can also kind of just tell them apart from the atoms in the bond. So electronegativity, that will be really important when it comes to covalent bonds, but in general, ionic bonds, those completely transfer, ionic bonds are the complete transfer of one or more electrons from one atom to another. So you can think of how originally you're asked to share that car with your sibling. That didn't happen. They just, used the car all the time and you never saw it again. So sharing is not caring. And usually it's between a cation and an anion. Usually it forms some type of salt. So cation, that's metal. Ion is a nonmetal. So you can kind of visualize that on the periodic table when you're kind of looking at a formula and then comparing that to the periodic table. Covalent bonds, those are when the valence electrons are shared equally between atoms. So these are usually formed between two nonmetals or nonmetal and a metalloid. Then there is metallic. Metallic, I feel like it's the easiest to identify. So we're mostly just going to talk about it on this slide right now. So metallic, that's the communal sharing of electrons or sharing and save electrons. Also, if you're more curious about that, I think it's somewhere in the lectures in the 20s is when those get talked about more when we're talking about conductivity. But basically, because of the way that they share all these electrons, that's why they can kind of move around, and why it becomes conductive is the electrons are just delocalized from the metal ions. So those you'll see only happen for the most part between two metals or maybe a metal and a metalloid. And the reason that all these things are important in reality is because even if you have two compounds that have the same molecular formula, depending on how the atoms are connected to each other, that's going to affect the shape, and the shape's going to affect how it moves in space and how they group together, and that will affect how they might interact with other other molecules or how they interact like with molecules in the body. That's how things become poisonous. Is, you know, the key just fits into that lock, and yeah, not necessarily where it should be, but it's where your body has it, and then it's not good. Anyways, I don't know why I'm trying to be funny today. I really shouldn't. Okay, let's continue. Energy. Okay, so bonding helps minimize energy and allows an atom to achieve a more stable energy state. So this is really awesome, really fun. Here we have two hydrogen bonds. Two hydrogen bonds are what's the word that I'm looking for? Non-metals. They're two non-metals, and that means they're covalent bonded. And then here we can see how it allows them to achieve a more stable energy state. So basically, when they are the appropriate distance apart from each other, the nucleuses aren't too close together or not too close apart, they can share the electrons without kind of repelling each other. So they want to ideally be right here, like this. They want to be like that cozy little distance apart. In reality, they probably will go back and forth, like kind of up and down between this spot, because like they move around a little bit. But they don't really like to be up here, because that's when the protons are too close together. That's when they start to repel each other. And that actually force them to come back down here usually. And then they don't really like to be over here because they're separate. They don't have that extra electron in their valence shell, and just kind of sad and lonely. So to get them over here, to get them to separate, that usually requires energy. I'm trying to think if there's anything else that we need to talk about with this. Yeah. Oh, yes. Okay, yeah. So, okay, they require energy. The energy is going to come from somewhere, usually it's their surroundings. So as their bond is being broken, then their surroundings will usually feel a little bit colder. But again, that's something that we'll go into more detail in this class later on. In fact, we just went over it. So electronegativity. Okay, so electronegativity, that is one of the trends that we need to remember. So the idea of this, super quick, is electronegativity is the ability of an atom to pull electrons in a bond towards itself. And in general, the trend looks kind of like, let's see which color will show up nicely in here. I think this will. So oh no, not that one. Let's do red. Okay. So as you go up a group, electronegativity increases. As you go down a period, electronegativity increases. Or you can just kind of remember this diagonal thing and just think this plus that equals this. Kind of like a triangle. That's how I put it down. It's like a triangle. So with these, by remembering the electronegativity patterns, you can kind of tell how likely an atom or a molecule, how likely a molecule would be to be polar, or also how likely it would be to be covalent or ionic, because here we can see. Okay, so this X isn't actually an X. It's a fancy Greek letter that is called septa, I think. So delta, septa, something like that. But anyways, if that, because this represents electronegativity, is less than 2, like the difference between the electronegativity of the two atoms, then it's going to be covalent. If the difference between the electronegativity of the two atoms is greater than 2, then it's going to be ionic, because that means one is a lot stronger than the other, and it has the ability to, I'm not sure if you just saw that my computer was low on battery, but it's on battery. That's why I got distracted for a moment. Anyways, but that means that one has a lot stronger electronegativity than the others. That allows it to steal the electron from the other one. On the chart, you can see that there are two little things that we need to keep note of. Let me flip back to this. There are two little things that we need to keep note of. I believe Dr. Mortensen said that we don't really need to keep track of them, or that it shouldn't come up too much, because for the most part, from now on, we'll have like this electronegativity chart on our exams. But I think it's important to at least like remember, at least in the back of your mind. So right here, you can see a little like hump where it kind of goes up in the middle with the metals. And then, so that's important to remember. This is the one that he said not to really remember, I think. Or not to really, well, he said to remember, but like not be too stressed about it. This one's the one that I feel like could trip a person up on an exam. Because over here, these are all part of group 18, and they all have full valence shells. Yay! Good for them. They must feel very successful in life. But basically because of that, they don't really care about sharing them or taking them or giving them up to anyone else. So they're not too interested in bonding. So they're just said to have an electronegativity of 0. And although they can bond with stuff, as we have learned in this class, they just don't really feel a strong desire to. This is my third time we're doing this part of the presentation, because the first time I got interrupted. The second time, my computer died, which is something that we talked about in the first version of this, was how my computer was low on battery, and then I forgot about that. Anyway, covalent bonds. We returned to this because we talked about it briefly previously, but as I mentioned on the other slide, they can be polar or nonpolar, depending on their difference in electronegativity. So in a general rule of thumb that we use for this class is if the difference of electronegativity between two atoms in the molecule is between 0 and 0.4, they are nonpolar covalent. That means they're really, really good at sharing, meaning that the electron will go back and forth between them and it would be fine. If the difference between electronegativity of the two atoms in a molecule, however, is between 0.4 and 2, that means it's going to be polar covalent, because one of them is going to be holding on to those electrons just a little bit more. So a good example that we have is right here with chlorine and chlorine. These are nonpolar. They're nonpolarly bonded because, I started thinking about later on in the slide what I was going to do. Because these basically cancel out. 3 minus 3 is 0. So then that falls in this range, so nonpolar covalent. So electrons are going to be evenly distributed. With these two, they are obviously different atoms. They have different electronegativity charges, which we saw on the last slide. On that table that has them all listed, that's where we get these numbers from. Those numbers on exam 1 are not given to us because that's when we're being tested on these trends. And usually we're just asked to look at trends and kind of based on that trend, what theoretically what should be more have a larger difference and so on and so such. But any hoodle-doodle-poodle for exam 2 and 3, then it usually is on there. But for these two, we have hydrogen, which has an electronegative charge of 2.1, and chlorine, which has an electronegative charge of 3.0. So 3.0 minus 2.1, that is 0.9, and like I've said, I guess not this time, 0.9 is between 0.4 and 2.0, so it's covalently bonded. That means that one side is going to hold on to those electrons a little bit longer. That means that this side with chlorine, because it's bigger, as far as like electronegativity charge, and the electrons are going to be more attracted to this nucleus, hang out over here more, and make this side slightly more negative, as we see right here. And this side is going to be slightly more positive, as we see right here. This is important because, for one thing, it reminds us of the dipole moment, which quantifies the extent of the charge separation, and we can test for this. So basically, because of the difference in an area that does not have an electrostatic field, then the molecules, they just kind of float around, do their thing, be happy, live their lives. But as soon as the electric field is flipped on, the negative end of the atom is going to orientate itself towards the positive side, and the positive side of the atom of the molecule is going to orientate itself towards the negative side of the electric field. Yep. Anything else I need to go over? Nope, not that I can really think of. Oh, yes, actually there is. I briefly looked at my notes. Do y'all remember this little arrow? This is an important little arrow because it indicates the side that is more like negative. So yes, just remember that. That's going to come up later as well. And yeah. The practice. So I wanted to give you a little bit of practice, like differentiating between these different molecules. So we have a variety, and some of them are going to be ionic, some of them are going to be non-polar covalent, and some of them are going to be polar covalent, and then others are going to be, let's see if I can write with this. Anyways, they're going to be metallic. Going to be metallic. Anyways, as far as like the bond types. So we have NaCl here. So if you look up here on, I'm not sure if you can see the little drawing thing unless I'm drawing with it. So here. So if you look on here, so here is, oh yeah, I always get lost. Here's Na, so that's 0.1, and then Cl is 3. So let's flip back over to drawing utensil, and let's, so 3 minus 0.9 is 2.9. So that is going to be ionic. Okay. There we go. I don't know how people write with this. Kind of look like a kindergartner, but that's fine. Hopefully you guys find this funny. Yeah, that's 2.9 because it's obviously greater than 2. That's going to be ionic. H2O, we've talked about it a lot in class. So, I mean, hopefully you guys could just tell from looking at it, but if not, we can also use this table. So for this, we're just going to look at the bond between one H and one O. So one H, that's 2.1 minus O, which is 3.5. If you look on the table, 3.5. Obviously, this is going to be negative. We just need the difference, so it doesn't matter which orientation it's in. So it's going to be 1.4. And if it is 1.4, then it is between 0.4 and 2, so it's polarly covalent. Yep, this is kind of turning wonky, but then we have CH4. So we're just going to look at the difference between the 1C and one of the H's. So that is, let's see, So like we found one of the H's before, so that's 2.1. And then carbon is 2.5. So mental math, that is 0.4. And in this case, that makes it nonpolar covalent. Non-polar covalent. Then we have tin right here. I will keep writing some stuff, but not for these two. Okay, so we have tin right here, so we can look on here for tin, but don't feel like you have to, because tin is metal. I always think about those like World War II ads when they're like having the like little boys go out and like collect scrap metal and tin. But so it's metallic. So this bond is metallic. Iodine. Okay, so I just put the name for this. Iodine is one of the ones that you could just look at as, oh, I do not want that. I2. So it's just bonded with itself. So iodine, that has an electronegativity of 2.5. Now, if you take 2.5 and subtract 2.5 from it, the difference is nothing. There's no difference. So it's going to be non-polar covalent. And for basically, for anything that you see, just iodine. Or for anything that is just bonded with itself, so it's like O2 or H2, then there's no difference between the electronegativity, so it's just going to be 0, and just going to be nonpolar. CO. So CO. Wait. I'm going to say what it stands for. Carbon monoxide, I believe it is CO. Anyway, so that's 2.5. That's 3.5. So if you put 3.5, minus 2.5. This is fun. That's equals 1. Which one is obviously between 0.4 and 2, so that's just going to be polar covalent. Then we have NO2, so just look at the N, one of the O's, so N, that's 3, O, it's at 3.5, quick math, that is 0.5, and 0.5 is going to be between 0.4 and 2, so that's polar covalent. And then mercury. Mercury, what do you think mercury is? Actually, you probably don't want me to play guessing games because you probably just want to get through this video. But anyways, mercury is another metal. Sometimes I feel like it's easy to forget about mercury because it likes to be cool and be liquid at room temperature and not be like all the other metals. But it still kind of follows the rules as far as bonding. So it's also metallic. It's a metallic bond. So felicidades, you got through this practice with me. Yay. Okay, last slide. Let's go. Okay, so vibration modes. I put this back here because, to be honest, I wasn't really sure how to put it like with other ones because I felt like all the other stuff needed to be explained first. But basically, vibration modes are kind of how the how the atoms like move, like due to the bonds, like in relation to each other. So I have this cool little animation that we can watch real quick if it works. Oh, maybe it won't work. That's unfortunate. Basically, it's just a visual though. And I can kind of just explain it. So there's 4, but we really only need to worry about 3. So there's the symmetric stretch. So this symmetric stretch, like if you imagine a slinky, it would just like kind of pull in and out like that. There's the asymmetric stretch, which kind of just goes back and forth. But like this part will remain stationary, and so like it would just be like those going back and forth, if that makes sense. And then the bending mode, that is just kind of like a bird flapping its wings, or child flapping their arms trying to mimic a bird. So this is just up and down. And this bottom one that wasn't really talked about in class, honestly, these two are the same. This is just like on its side, so you can't really see the up and down motion, or tell that it's going forward and backwards, except for like how these things are moving. But that's just another way of like looking at it in space. But this is important because basically it affects the how things are absorbed. Like how energy is absorbed into an atom or molecule, and basically because of the wave-like pattern of these, then that will affect what frequency of radiation that it can absorb. So so basically it will absorb radiation if the frequency matches delta E of electron energy levels, and by molecules absorb they'll absorb infrared radiation if is that a typo? Oh, I apologize. That should be radiation. If frequency matches frequency of vibration of IR active modes. So in class we talked about how that would the impacts it would have on the environment, and basically it plays a role in the greenhouse effect, and specifically actually CO2. I actually think that's the example that we had in class too. I did not realize that when I was putting this together. But CO2, that can affect the greenhouse effect. Because basically CO2 likes to absorb infrared radiation just because of some of the ways it can like move around. It can do that, but as it is releasing it, then it can release it back down to the Earth. But the Earth doesn't really want it. In fact, the Earth releases infrared radiation to just get it away back into space, because originally it comes from the sun. And if CO2 is there, it's just going to trap it. And although the CO2 were like release some of it eventually, like it won't release it like upward, or kind of just like release it in any direction, so like back down to Earth. And so like we just keep accumulating heat. And then we have 40-year-old men just complaining about how the AC can't be low enough. But yes. And that is the end of this presentation. Like I said, I would recommend going back through it and just like making sure you can explain to yourself everything that we talked about. Let's see. I don't think we talked about lattice energy real quick. Okay, give me a moment. I'll explain that super quick. Now we're back with this last slide. Yes, I just wanted to make sure that we cover this. So lattice energy, so basically that's the energy required to break apart the lattice, which is kind of like the crystallized like formation of molecules. They're just like nice and evenly stacked. So basically the way that this is like determined or thought about is they hold on to each other like they'll hold on to each other like more. Okay, so the amount that they hold on to each other is determined by like the size of the ions. So with that, you just have to remember that as you go down a group, the size of the ions decrease, and as you go across a period, the size of the ions decrease. Let's see, did I say that correctly? Yes, yeah, down a group they increase as in like the radius of the molecule like gets bigger, and as you go across the period they get smaller. So basically they kind of, for the most part, they like follow the same trend for electronegativity, but in like the flip, where like if you kind of do that like arrow across, then that will then get them be getting, it would be them getting smaller rather than them getting larger, like with the electronegativity. So that's important to remember. This follows Coulomb's law. So there's a formula. This kind of already has it kind of filled out a little bit. But I believe this video is on Khan Academy, and it's really helpful if you guys want to learn more about that. But basically, so basically the difference between the atoms that will like determine how strongly that they're holding on to each other and how much energy is required to break them apart. And I believe that is everything. Okay guys, good luck.